We are now going to start with the discussion of synchronous machines. So how is the basic operating principle different from the induction machine? If you consider the stator is going to be same as what you see in the induction machine. It is going to have a 3-phase winding, and these are spaced 120 degrees apart, and the currents flowing through them are 3-phase balanced currents. Okay, so what does this mean? This means that 120 degrees apart with respect to time. So the synchronous machine also, it is going to have the same stator structure, but the difference comes in the rotor circuit. What happened in the induction machine? There was a 3-phase winding. Just like a stator, there was a rotor winding, same 3-phase winding spaced 120 degrees apart. Okay, but here in the synchronous machine you are going to have a DC fed rotor winding. So how is this going to affect the operating principle? How is it going to be different from the induction machine? So we will start with both the generator as well as the motor. First, if you take the case of generator. So what does a generator do? It is going to take the mechanical input and give electrical output. So in a synchronous machine, how is it going to happen? The mechanical input is given by the prime mover, right? So this is going to turn the rotor. Now the rotor is an electromagnet. Why is that? Because there is a DC field circuit which is energizing the rotor winding. So this is going to give an electromagnet. Now what is the combined effect of the rotor turning and it being an electromagnet? This is going to give rise to a rotating magnetic field, right? You can visualize the rotor. This is the rotor, let us say. Now say because of the DC field circuit, we have the north and south poles. Now what will be the direction of the magnetic field? It will be from south to north. Now this rotor is also rotating. So that means this vector that is there, it will keep rotating. But one important point that you have to see here is the magnetic field is stationary with respect to the rotor. Okay, so that means if you consider this to be point A on the rotor, then the north pole is always going to stay at the point A only. Okay, but in induction machine that was not the case. The magnetic field, the rotor magnetic field itself was rotating with respect to the rotor. So now we have the rotating magnetic field. How will it produce the electrical output? So we have seen that a 3-phase setup, which are 120 degrees out of phase with respect to time as well as space, will give a rotating magnetic field. Similarly, the vice versa is also true. That means if you get a rotating magnetic field, then this can induce 3-phase balanced currents in windings which are placed 120 degrees apart. Okay, so this is how in the synchronous generator you are going to get a electrical output. Now what about the case of synchronous motor? In the motor, what is the principle? You are going to get electrical input which is going to give rise to a mechanical output. So 3-phase supply will be given to the stator windings. 3-phase supply is given to the stator windings. This is going to result in a rotating magnetic field, just like in the case of induction machine. And also the DC field circuit, as it is, just like in the case of generator, it is going to energize the rotor winding. So that means whether it is a motor or a generator, the DC field circuit should always energize the rotor winding. That is not going to change. Okay. So this is going to give rise to an electromagnet. Now what will happen to an electromagnet when it is placed in a rotating magnetic field? It will try to align itself to this rotating magnetic field, and that is how the rotor will start moving. So you can write electromagnet in the presence of a rotating magnetic field will try to align itself to the moving field. So this tendency is what is going to make the rotor turn. Therefore, rotor will rotate. Okay. So this is the basic principle of the synchronous machine. How a generator operates and how a motor operates.